Hello students, in this video we'll see how to compute the center of mass of a rod that has non-constant density. So if we're given a rod, and this rod is going to be a one-dimensional thing with density rho of x on the interval a to b, we wish to find the center of mass. And so what we can do is we can recall what the mass is. So the mass, the total mass, we saw in a previous video, m is the integral from a to b of rho of x dx. The integral of the density between a and b is the total mass. Now, let's think to a simple situation. If I have a mass m1 at a particular point, and then I have a mass m2 at a different point, then the center of mass lies somewhere in between there. Just two masses. The center of mass I'm going to call x bar. And what we know is we know that in order for this to balance, if I call this distance over here d1 and this distance over here d2, this system will balance. This will be a fulcrum point. This balances if and only if m1 times d1 is equal to m2 times d2. Now, we know what d1 and d2 are. So d1 is x bar minus the location, call this point over here x1 at location x1 at location x2, minus x1 must be equal to m2, and then this will be x2 minus x bar. Now we'll solve this equation for x bar. So what this tells us that I have a m2 x2 over here, and I have a negative m1 x1 over here. So what I'll do is I'll bring all the m1s and the x1s to one side. So m1 x1, m2 x2 is equal to, and then now I'll bring all of the x bars to the other side. So what I'll have an m2, and then I'll have a minus plus m1 x bar, and that tells us that x bar is equal to m1 x1 plus m2 x2 over m1 plus m2. Now, the same argument works for any number of masses. So I can extend this from two masses to any arbitrary number of masses. So in general, the same argument shows that x bar, the center of mass for n masses, will be m1 x1 all the way down to mn xn, all divided by m1 plus m2 plus mn. And again, we can realize this is a Riemann sum, right? So this is really, in disguise, a Riemann sum. I can realize this is a Riemann sum. And as n goes to infinity, the center of mass becomes the integral from a to b of x rho of x dx over the integral from a to b of rho of x dx. We see that the denominator is exactly just the total mass. So this over here is just the total mass. And what this is over here is the form of an expected value. It has x times the density. So this gives us a formula for the center of mass. And so in particular, what we could say, we could look at a simple example of this. If rho of x from our previous example was just x for x between 0 and 1, then x bar, the center of mass of this rod, will be the integral from 0 to 1 of x times x dx over the integral from 0 to 1 of x dx. So this top thing is x squared. That's going to integrate to a third. The bottom is going to integrate to a half. And so what we have is we have 2/3. And so what this is saying if I have a linearly growing density, here's 1, here's 0. If there's virtually no density over here, then what you need to do is you need to balance To balance this, you need to put your finger at the 2/3 point, and that will balance this rod, which has a linearly growing density between 0 and 1. Thank you very much.